Well, at the end of the last video, we were looking at Snell's law. And Snell's law looks at how light is refracted into different mediums. When we kind of continue on, we start to look at not only is light refracted, but it can also be reflected at the same time. Okay, so a lot of our light rays, as we look at them going from one surface to another, will not only come in and refract. So if this being my surface here, light comes in, it refracts, okay, but it also reflects. And so we start to look at that. Now, maybe there's a couple of you that have been swimmers or things like that, and if you ever go into the swimming pool and you're under the water and you're trying to look out, it's like you can look out and see up above you, but then there's a point out there where all of a sudden it's like it looks more like a mirror and you can't see out anymore. This is what we call total internal reflection. Now, it's a concept that's used widely in the world of fiber optics. So like a strand of fiber optics is nothing more than a strand of like glass in which they're trying to send light down through it, and the light itself, when it hits the edge, is refracted, or I should say reflected back. It's not allowed to refract out into the air. So light travels through that essentially tube of glass, and it can be bent and everything, so it's very flexible, and it's a nice way to send information. So we've gotten to the point where we can carry information on a wave of light. Okay. So how does total internal reflection work? If we kind of look at the picture that I've got here, this would be my light ray, and at this angle we can see straight out. So in other words, we transfer right out. If we start to vary our angle, we get a little bit of reflection and a little bit of refraction. Okay, so in other words, the light ray that we're sending gets kind of split into two pieces. So some of the energy gets refracted, some of the energy gets reflected. As you change the angle, you get to a point where you see more and more. Now again, we get to this 45 right here, so we get 45 in the reflected, but then we can see that our angle of refraction is getting extremely close to 90 degrees. When we get to a point to where the refraction angle is 90 degrees, that's the point at where we have what we call a critical angle. Okay, that's the critical angle, and this is again the angle of incidence. So the angle of incidence comes in, and all of a sudden it hits that point where the refraction occurs, but the refraction actually occurs on the surface. Okay, so in other words, we actually get the light following the surface. That's called a critical angle, and that's where we start to see no longer can we refract any of our light energy out. Any angle beyond that we see as internal reflection, and so we get this total internal reflection, and all light then is allowed to bounce in there. Again, something we use all the time in the fiber optics industry. Okay, it was a major change when we could develop lines to carry high amounts of information on light. Okay, and we'll probably see a demo of that tomorrow. The next kind of thing where we go when we look at light is we have to start to look at colors. Okay, this is again where we start to look at light as we see it. Okay, a white light that comes to us is a blending of a lot of different frequencies. So if you go back to the electromagnetic spectrum and you saw how the electromagnetic spectrum was split up into like that rainbow, okay? And so you had 400 nanometers to 700 nanometers, and so you had this range of wavelengths or range of frequencies that could occur. And all of these wavelengths and different frequencies essentially are saying that we have lots of different colors. So a color can be represented by a wavelength or a frequency. Now, if you blend all of these colors together, you get white light. Okay, the blending of all the colors is white. There are three primary colors when we start to talk about light, and the only three primary colors of light are red, blue, and green. It's a lot of the things that we adjust when we adjust the tint on monitors or on our color schemes within like Photoshop and things like that. So we're always adjusting our reds, our blues, and our greens because these, again, are the primary colors. Now, in elementary school, when you learned about primary colors, you were learning about the primary colors of paints or pigments, different than the primary colors of light. And they used to say it was red, blue, and yellow, and I think they did that because it was just easy to learn red and blue and yellow. But really, the primary colors of paints or pigments should be yellow, cyan, and magenta. Those should be the three colors. In fact, a lot of it, if you're buying cartridges for like a color printer, you're usually buying cyan, magenta, and yellows. In fact, and that's, again, you can go back into Photoshop, and if you're adjusting things in Photoshop, you can adjust the pigments as well as the lights. Now, why do we see something as green? Okay, this is a good question. So in other words, if I have a, let's see if I can get some color changing here. This is, it's how do you kill time when you're trying to do something with a very slow laptop? All right. I apologize. Maybe we'll just work in black. Or maybe we'll just slow down to a crawl with the computer. All right. So let's just say that I've got this little blob of something and this is green. Okay. At least our eyes perceive this as green. So again, our eyes have receptors inside the retinas. Okay. So our eyes have receptors that pick up green, that pick up red, that pick up blue, and essentially can blend these things together. But if we look at, say, a beam of light, okay, and this light is a white light, as this beam of light strikes this green object, whatever it is, this thing will absorb all of the red, okay, it absorbs red light and it absorbs blue light, okay, so these things are being absorbed, they're being taken in by this object. And then the only thing that's allowed to reflect back is the green light. Okay? So it's about what is allowed to be reflected back and what is actually absorbed. When you see something that's white, essentially you're able to reflect back all of those colors at the same time. When you see something as yellow, okay, let's look at this and say we want to see something that's yellow. Again, as our white light passes into it, okay, we absorb the blue and we reflect the red and the green. And because as the red and the green light come back out, they blend back together, and we actually see this then as that combination of yellow. So that's kind of how we look at these, how colors mix. We really like to look at this because when we start to look at refraction of things, we'll run light through, say, a prism, and a prism will give us a rainbow, and we run light through raindrops, and raindrops give us rainbows. And so it's all about taking the light as it passes into something, changing the speed slightly so that that white light can actually split itself out. And so that's why when we look at prisms, we see all of that rainbow of color. And we'll talk a little bit more about that here in a bit. Diffraction is another way to take light, or take a wave, I should say, take a wave and kind of look at it as a changing or a bending of it as it goes through. Refraction was when we actually hit a medium and we start to bend slightly, okay? So we hit it in a different medium and we kind of slow ourselves, and so that causes us to bend. It's one of those things that when we look at, say you're driving down the road and you have like a soft spot on the side edge, if your front wheel catches that, it it bends it, okay, because you're changing from, say, the road into the soft zone, and that's a change in mediums, and that's what forces you to go into the ditch. Well, diffraction is very similar to this, except that we're actually looking at a small opening or around a corner. So this is one of those things, like as you kind of close the door on your room at night, if you leave it open just a crack, it's like all of a sudden the room gets brighter, okay? The whole room gets brighter. So as that light starts to close down, we make a very small opening, and the light rays actually start to bend, okay? And so we start to see this pattern. And even if we look on the edges, we start to maybe even see a little bit of color change along the edge. And so even like it's anytime we bend things, we start to get that little bit of color. In fact, as light tries to go around something, it'll start to separate into colors as well. And so this is where we kind of see like a halo effect around people if we have light sources around them. So it's one of the things that we look at when we're doing photography. Now, the biggest thing that they did is they did this big experiment, and it was called the double slit experiment. And so they started it with light, and they looked at what happens as light passes through, say, two openings. So you get two openings where the light comes through, and you're getting a pattern, okay? And these two patterns will have intersection points. And that intersection point is a point of interference, okay? So we get like a constructive interference and we get a destructive interference. And where we get constructive interference, that's where we start to see some very bright light sources, okay? And so we're intensifying it because, again, you're taking the wave energy from one, you're taking the wave energy from the other, and you're mushing the two wave energies together. And that's how we get constructive interference. Now, in the dim spots, okay, so as the light was passing through, we get the other areas. The other areas are where we are taking like light that's in one range and light that's in another range, and the two ranges cancel each other, and so it's like we're getting destructive interference. Okay, so that's where we're looking at our interference patterns. Now they extended this out to start to look at electrons, and they found the interesting thing was, of course, that the electron, which behaved like a particle, produced a pattern not like this going through, but it actually produced a wave-like pattern when it went through the double slit. Then, of course, we started to try to observe it, and we found that the wave function collapsed, and so there was a whole strange behavior with electrons, and this is why electrons have properties of both waves and particles. And we also find that light has a similar characteristic. It acts as a wave, and it also acts as a particle. It's a whole other discussion for a quantum talk. We have another concept here that we like to talk about when we talk about light. We like to talk about its polarization. And polarization is just this. As light comes out, so in other words, let's say we've got the sun out here, and the sun is actually emitting light. The light happens to be vibrating in all directions. And then we look at it, and we're maybe on, say, the water. So this is our water, okay? And as the light rays vibrating in all directions hit the water, they kind of come out as a very much certain plane, okay? So they're coming out as a plane instead of coming out in all directions. So here we have light coming in, and it very much hits a plane. This works on snow as well as it does on water, but essentially we're making the light all go one direction. My analogy to this is like we're passing it through a fence, and blocks all other directional vibrations and only allows certain directional vibrations to come through. Now what we do is we have a tendency to wear sunglasses in this instance. So we have sunglasses when we go fishing on the lakes. We have polarized lenses that we put in our ski goggles. We have things that essentially are going to take and block out most of that light ray that has been polarized by hitting that one part. If you actually have a pair of polarized sunglasses, if you have two pair or something, if you put the two lenses together, you can actually see how they change. And that's what we're looking at when we say we have two different angles of the picket fences. The biggest place where they use a lot of polarization is they'll use it in stress testing. And so I'll probably do some demonstrations with some polarized filters as well. I think this is the end of our topics. And on light, I'm just going to see if I can switch one more. Yep. And so we will talk more tomorrow.